Hello guys, and welcome to another video. So we are treating another examination question on state space analysis. So this is the prominent double mass string system, and this is the question. So a mechanical engineering system comprises of two masses m1 and m2 and two local springs of constants k1 and k2 shown below. So this is double mass spring system, and this is the question. It said if an applied force F naught sine omega t is applied to mass m1 or m2 vertically downwards. Okay, so derive the equations to the non-homogeneous form. X of t is equal to ax of t plus g of t. Of course, we know these are vectors. Okay, so vectors, and we're going to dive into the solution of this problem quickly like this. So one of the key to solving this problem is learning how to understand the free body diagram on each of the masses associated in this system. So I'm just going to reproduce the system here. So we have a system like this, and we have a spring, we now have m1, and we now have another spring, we now have m2, we now have the applied force. Okay, that's, let me call it our f of t. Okay, so this is m2, and m2 actually faces a displacement x2. Of course, some people use y. Okay, so whether you use x or you use y, it doesn't matter, but it's more professional to use y since we're dealing with vertical motion. But don't worry, x and y still means the same thing. So you now have your m1 undergoes a displacement, okay, which is x1, and this is the k1 spring constant, this is support, and this is the k2 spring constant. So you have this particular system of forces. So we are going to start by analyzing, okay, the forces. It's normally good to start with the outermost mass. So analyzing forces on m2. So to analyze the forces on m2, you need to what? Get the free body diagram, okay, on m2. So the free body diagram on m2 is what we are going to analyze. Now this is your m2. So you can see that the applied force points in this direction. Now the direction of pointing of the applied force will be taken as our positive direction, okay, to be taken as our positive sense of motion. So that is, as you can see, is also the direction of the displacement. The direction of the displacement is in the direction of the applied force. So now when you apply this particular force on this mass, we have a resistive force that is acting, okay, which is the force generated in this particular spring, and that force acts in the opposite direction. Is called the restorting force. So the force is proportional to the extension that is generated in this particular spring K2. But the big question is, what is the extension generated in this particular spring K2? Now this is a very, very tricky system. So big question. So what is the extension generated in this particular place? Now the extension generated is actually going to be what? X2 minus x1. So this is actually relative. Okay, the extension that is generated here is relative, while the extension that is generated in this particular place is x. The extension, that is generated in this particular spring is x1. The extension that is generated in this particular spring is x2 minus x1. Okay, so the best way for me to explain this particular stuff is relative motion, okay, relative velocity. So assuming you have two cars moving together like this, You have two cars moving together, car A and car B. Now, car A is moving at a velocity of 40 meters per second or 40 kilometers per hour or miles per hour. Car B is moving at a speed of let's say 60 miles per hour, okay, or meters per second. Now, if I ask you to calculate the relative velocity of this particular two cars, you can tell me that the relative velocity is actually the velocity of what? VB minus VA, which is going to be 60 minus what? 40, which is going to be what? 20 meters per second. So they are just trying to tell us that with reference to car A, okay, the car B is traveling at 20 meters per second. So car B's motion is just as if I'm starting from a particular point, and the point is the observer A, and I'm moving with a velocity of 20 meters per second. But in essence, car B is actually moving at 60 meters per second. But because car A, this reference point, is also moving, you cannot just say that the velocity of car B with respect to A is 60 meters per second. It is actually the relative velocity between both of them, which is going to be what? 20 meters per second, with reference to this observer. And that's exactly what is playing out here. Relative velocity is playing out here in terms of x2 dot minus x1 dot, that's the first derivatives, and relative displacement is also playing out here, in the sense that when you stretch these particular masses, remember x1 is also moving and x2 is also moving. But since x1 and x2 is moving, therefore the relative displacement of x1 with respect to x2 is actually going to be x1 minus x2. But however, if we are calculating for x1, we are calculating for x1 with respect to the origin. So x1 is moving with respect to a stationary point. Okay, that's why the displacement is just x1. But x2 is moving with respect to x1, which is already moving with respect to the origin too. So you have to know that the relative displacement and the relative velocity at this particular point here is actually x2 minus x1. Okay, so you will very much need to understand this in order to proceed with the rest of this particular problem. So now that we've understood the relative displacement or the relative extension at this particular point with respect to the two masses, then we can now go ahead and evaluate our free body diagram as follows. Ctrl Z, Ctrl X. So let me just crop and paste this analogy somewhere here, so that perhaps you might want to make reference to it in the future. So we've assumed that or we've actually stated that the extension, okay, of this particular mass with respect to the first mass is x2 minus x1. Is that okay? So remember the restoring force, when this force is pulling m2 down, the spring will try to what? Take m2 back, and that force is proportional to what? The extension, which is what? X2 minus what? X1, and the constant of proportionality will be the spring constant in this case. So this is the force that tends to what? Restore this guy back. So if we take the summation of forces according to Newton's second law, summation F should be equal to what? Mass times acceleration. Take note, displacement is in this direction, so x2 is in this direction, therefore acceleration will also be in this direction. Acceleration is the second derivative of displacement, x2 dot dot. Okay, so x2 dot is simply dx2 by dt. X2 dot dot is d2x2 over dt square. So when we are working with time derivatives, to save ourselves the stress of writing dx dt and d2x dt square, we just use the dot notation. So since the direction of the force is actually in this direction, the direction of the displacement and the acceleration will also be in this direction. So this is the free body diagram, and the summation of all forces acting on m2 should be proportional to what? The rate of change of momentum, or in other words, mass m2 times acceleration, which is in this case is x2 dot dot. Is that okay? So let's calculate summation f. So summation f is actually calculated by saying you have to sum applied force and you have to subtract resistive forces. In the end, you still equate it to your m2 times acceleration. Is that okay? So don't forget this. So this is how we actually roll. So sum of all applied force, in this case we have our f of t being the applied force, and the resistive force is actually the spring constant times the relative extension, which is going to be what, k2 into x2 minus x1. Then you now have equal to m to x2 dot dot. So this is what we have. So if we rearrange it, we'll have m2 x2 dot dot. Okay, and we now have plus k2 into x2 minus x1 is equal to f of t. So this is equation 1. So this is the equation that is governing the motion of m2. Okay, m2. Then let's analyze free body diagram on m1. So fbd on mass 1. So the same thing is happening. On mass 1. So this is mass 1. Okay, we have the direction of displacement, which is x1, and we also have the direction of the acceleration, x1 dot dot. That's the second derivative of acceleration. So this is our m1. Now we should know that m1 is actually undergoing two forces. Now we'll start with the resistive force. The resistive force is acting in this direction, and this time around it is proportional to the extension. So the extension that we have on this place is just x1. So the resistive force is going to be what? K1 x1. Okay, so what force is actually pulling m1 down? So what force is pulling m1 down? This force pulling m1 down is the same force. Okay, is the same force that is actually pulling m2 backwards. So it's the same force. So there is tension here. Tension is felt here. So the force pulling m2 down is the same, the force that is actually trying to restore m2 back to its normal position is actually the force that is pulling what, m1 down. So you can actually give that same magnitude, which was k2 into x2 minus x1. So the restoring force on m2, okay, in this other direction is actually the force m1 feels in the opposite direction. So this is how we get the free body diagram of forces acting on m1. And as usual, we now apply our summation. F is equal to mass times acceleration, okay, x1 dot dot. So summation F is sum of all applied forces, which in this case we are now going to have our k2 into x2 minus x1 and minus sum of restorative forces. So the restorative forces is k1 x1 and is equal to what, m1 x1 dot dot. So when we rearrange this equation, we'll have m1 x1 dot dot minus k2 into x2 minus x1. Then you now have plus k1 x1 is equal to 0. So for the first mass, it will be equal to 0. Now, one thing professionals do is that when they get to this point, they will say m1 x1 dot dot, okay, then plus k2 into x1 minus x2 plus k1 x1 is equal to 0. So what they just did was they just factored out the minus sign. When you factor out the minus sign, x1 and x2 will change position. The minus sign will now change this one to plus. Is that okay? So everything will now be plus. Is that okay? So this is the equation of motion that is governing the second that's mass 1. So we have this as equation 2. So we have two systems of second order differential equations. Now when you have two systems of second order differential equations and you want to obtain the state space representation of that system, it is going to decompose. Each of the second order system will decompose into two separate state space system, or we can combine the whole state space representation into one state space representation containing 4 systems of linear first order homogeneous differential equation. So in order to do that, we're going to bring our 2 equations together. So bringing equation 1 and 2 together, you have your m2x2 dot dot, okay. Equation 1 was m2x2 dot dot, okay. Then we have plus, we have k2 into x2 minus x1 is equal to f of t, okay. And we had m1 x, we have x1 dot dot, and plus k1 into x1 minus x2, and plus k1 x1, okay, equal to 0. Equation 2. So this is 2 system of what? Second order differential equations, which altogether will decompose into 4, okay, systems of linear non-homogeneous, okay, equations. So let's see how that is possible. Okay, we now want to come to a very important stage, which is the stage of choosing our state variables. We are going to choose our state variables so that we'll generate 4 systems of linear homogeneous differential equations. So we are going to say let's, okay. So let's z1. So z1, the first state variable, will represent the displacement of our first mass. Then z2 will represent the velocity of x1, okay. So z2 will represent the velocity of the first mass. So in the same way, z3 will represent the displacement of the second mass, and finally z4 will represent the what? The velocity of what? The second mass. So when you see me put a dot, I mean first derivative, that's the x1 dt. So displacement velocity for mass 1, displacement velocity for mass 2. So this is my state, or my choice of state variables. So remember that with these state variables, you'll be required to find your z1 dots, z2 dots, z3 dots, z4 dots, okay. You'll be required to find this representation, and this will give me some 4x4 matrix, which I don't know what is going to be in this 4x4 matrix, but I know that the states here will be z1, z2, z3, z4, okay, then plus inputs. So this is how our state is going to look. So we are going to use the information from this particular systems of equation that we have, okay, to get and populate our state matrix. Meanwhile, we should know that z1 dots, okay, z1 dots will be equal to, so z1 dots, as you can see, is corresponding to x1 dot. If you differentiate both sides, it will be x1 dot, and this is just simply z2, okay. So z1 dot, that's the derivative of the displacement, is going to give you the velocity, okay. So that's z2 velocity. Z2 is the velocity of this state. So z2 dot is going to give me x1 dot dot, and I don't know what x1 dot dot is yet, but I'll find it out later. Now similarly, z3 dot is going to give me the derivative of x2 dot, which is z4, okay. Look at it here. If you differentiate z3, you will have your z3 as the derivative of what? Very good. X2 dot, which is going to give you z4. That's another way of saying the velocity of the second mass. Now if you now differentiate z4, dot, you're going to get x2 second derivative, and second derivative is what we are going to find out on the equation. So our 2 points of concentration now to resolve this particular matrix is what is the second derivative of x1, and what is the second derivative of what, x2. So if we can find these two, we've gotten our matrix. Is that okay? So we're going to work towards doing that now. So I'm going to copy these two equations again, and we're going to find and conclude this problem, find the solution to this problem. So Ctrl C and Ctrl V, like this. So to solve this problem, so you need to recall that we chose, okay, z1 to be x1, we chose z2 to be x1 dots, okay, so we chose z3 to be x2, and we chose z4 to be x2 dots. So what we are going to do is we're now going to start replacing all these positions, okay, with the corresponding z. You're changing from x to z, so change from x to z domain. So this is not anything related to the discrete transforms, z transforms. No, it's just ordinary use of variables. Someone, instead of using z, would have used q and all, and so on and so forth. Is that okay? So you're changing from x to z. So this is how you're going to do it, starting with equation 1. So from equation 1, so from equation 1, you can see that our interest, remember our interest is wanted to find, we already know that z1 dot will be the velocity, right? Z1 dot will be the velocity of the first mass, which is z2 in terms of z. Then z2 dot will be what, x1 dot dots, when you differentiate both sides, and we don't know what it is, but trust me, we can make x1 dot dot the subject of the formula, and we'll be able to find an expression for z1 dot. So similarly, you can actually see that z3 dots will be equal to the derivative of x2, which is z4, and if you differentiate z4, you're going to get x2 dot dot, which we can actually obtain from equation 1 by making x2 dot dot the subject of the formula. So let's start with equation 1. So from equation 1, okay, we are going to make x2 dot dot subject. So that will give me m to x2 dot dot is equal to minus k2 into x2 minus x1. Then you now have plus f of t. So if you divide through by m2, so x2 dot dot is actually going to be, let's just say, minus k2 over m2 into x2 minus x1, then plus 1 over m2 f of t, like this. So if you do it like this, then you can now convert from x to z. Okay, now you know that x2 dot dots in terms of z is z4 dots. Is that okay? So you now have your z4 dots is going to be minus k2 all over m2 into my x2. So what is my x2? My x2 is z3. Okay, so we're going to do it carefully. Z3 minus, what is my x1? So my x1 in this case is what? Z. Is that okay? So you have your what? Z1. So your x1 is z1, as you can see here. Then you now have plus 1 over m2, you have your f of t. Is that okay? So if we open up this bracket, you have your z4 dots to be equal to minus let's arrange in terms of descending subscript of z. Minus times minus is plus, so we now have plus k2 over m2. We have z1, and we now have minus k2 all over m2. We have z3, and plus 1 all over m2, our f of t. Remember that f of t is the f naught sine omega t. So I'm just going to consolidate it in f of t for now. So we've gotten an expression for z4 dots. Okay, so an expression for z4 dot. Now let me tell you the secret of this particular stuff so that I'll save you much time. I know I'm doing a lot of explanation. The secret is after you convert all this, make all these assumptions, okay, changing of states or declaring of your states, okay, your state variables. All you just need to do is to find the z2 dot, which is x1 dot dot, and z4 dot, which is x2 dot dot, and you're done with this problem. That is just what you need to do. So in any mass spring problem, your objective is to find x2 dot dot in terms of z and x1 dot dots, okay, in terms of z. So now that we've gotten z4 dots, okay, so let's find this one, and you can always find this one from equation 2 while you can find this one from equation 1. So let's go ahead now. From equation 1, equation 2, sorry, you will have that your m1x1 dot dot plus k1 into x1 minus x2, okay, plus k1 x1 is equal to 0. I hope I got that right. Very good. So I got that right. Yeah. So we can now start doing the substitution. Or first of all, let's make this the subject of the formula. So x1 dot dot mx1 dot dot is going to be negative k1 x1 minus x2, and you now have minus k1 x1. Is that okay? So when you take it over to this side, to this m1, when you divide through by m1, you have minus k1 over m1, you have x1 minus x2, and minus k1 x1 all over what? m1. Okay, now see what is going to happen in this particular case. What did I do here? Okay, is this k1? No, this is not k1. I think I made a mistake. This is k2. I've made a mistake all from the beginning. And you guys must have been confused. I'm sorry about that. So okay, this is where I made the transitions, right? Yeah, I think from here, this is a k2, not a k1. Yeah, I think I've corrected it now. So please, I'm sorry about that. The free body diagram is k2, as you can see. So I don't know why I put k1. So it's k2. Yes, k2, please, because it's the same force. The same force that this guy feels, the resulting force k2 x2 minus x1, is the same force that this guy feels in the opposite direction. Okay, that's the force that pulls it down. So back to where we stopped. I've corrected it, so I just need to change everywhere that I put that equation. Yes, k2, yes, k2. Right, so I think we're good to go. So if I solve a little further, x1 dot dot is going to be, you can decide to collect these two together, so you get minus k2 over m1 minus k1 over m1 all into x1, then you now have minus k2 over m1 all into x2 when you factor these two together. So you now have your x1 dot dot is something like minus k2 plus k1 all over what? m1. You now have x1, then you now have minus k2 over m1, x2 like this. So you can now make the changes. So x to z. So your x1 dot dot, remember what x1 dot dot is? Your x1 dot dot is your z2 dots. Is that okay? So x1 dot dot is your z2 dots is equal to minus, you can call this one k1 plus k2 all over m1. So your x1 is your z1 and minus k2 over m1, and your x2 is actually going to be what? Your z3. So that's it, not your z2. So your z2 is the velocity of what? x1. Then z3 is displacement of x2, and z4 is the velocity of x2. Okay, so when you choose it like this, you've now gotten your z2 dot. So in summary, okay, we are going to align all of them like this. So my z1 dots was equal to z2, as you can see from this particular place. My z1 dot is equal to what? Z2. And how did we get it? Just differentiating both sides. Differentiate here and differentiate here, you get z1 dot is equal to x1 dot, and x1 dot is equal to z2. That means z1 dot is equal to z2. Remember, the aim is to convert every z dots in terms of z. Okay, so you're eliminating every appearance of x and you're converting it to z terms. Is that okay? So that's what you're doing in your state variables. So your z2 dots is what we just calculated now. Your z2 dot is minus k1 plus k2 over m1 into z1 minus k2 over m1 into what? z3. Is that okay? Then your z3 dots is going to be what? As you can see, z3 dots is what? z4. z3 dots is z4. So z3 dot is z4, you have z4, and finally your z4 dots is what we got up there, and this is going to be the full equation. K2 over m2 z1, k2 over m2 z1, I hope that's positive. Okay, and minus k2 over m2 z3 plus 1 all over m2 f of t plus 1 over m2 f of t. So this is the summary of our system. We can now convert this system into the matrix as follows. So it implies our z1 dots, z2 dots, z3 dots, and z4 dots, which represents the state space representation of our system, is going to be, so in the equation z1, the only term that you have is z2. So I'm going to have my terms like this. Sorry, let me shift it like this. So we have our state variables z1, z2, z3, and z4. And we now have our inputs. Guess what our input is? Our input is the input force, F of t. Is that okay? Our input is the input force. So let's start representing it now. So in z1 is equal to z2. You can see that z2 is the only equation. So this is a 4x4 matrix. So z2 is the only one, and the coefficient of z2 is 1. So there's no z1, 0. z2 exists as 1. No z3, no z4. So you have 0, 1, 0, 0. So z2 dots. So z2 dots, the coefficient of z1 is minus into k1 plus k2 over m1. So you're going to put it there, squeeze it, minus k1 plus k2 over m1. Okay, then is there a z2 there? There's no z2 in this equation, so it will be 0. but there's z3, right, giving us a coefficient of minus k2 over m1. So you now have minus k2 over m1, and finally z4 is 0. So z3 is going to be what? Only z4. So z4 is the only coefficient there with a coefficient of 1. There's no z1, no z2, no z3, only z4. And finally, for z4, we have our z1 to have a coefficient of k2 over m2. Z1 has a coefficient of k2 over m2. So z2 does not have any coefficient, which is 0. z3 has a coefficient of minus k2 over m2. Now have minus k2 over m2, and there is no z4, but we have an f of t term. So you have what? 0. Now notice that in all these particular equations, f of t does not occur. In other words, we have 0 f of t, 0 f of t, 0 f of t. Now the only one that has an f of t that is non-zero is the last one, which is having a coefficient of 1 over m2. So that is going to come here, 1 over m2. Why the rest of them be 0, 0, 0, like this. So this is the state space representation of your system in this way. Yeah, and that's all. So this one was pretty long, but I hope you understood the procedures. Go back to it and let me just recap what we did. First of all, we brought out the free body diagram of each mass and we analyzed the forces acting on them. We applied Newton's law. We got our second order equations, that's two system of second order equations. When you have two system of second order equations, each of them will break down into 2. Okay, so when you combine it, it now gives you four system of homogeneous linear differential equations, which we have here. So we converted our state variables into z, the z term. We could use x, we could use q, we could use any letter. Okay, but the most important thing is know how to do the transition, know how to assign your states. Our state is z1 representing the displacement and z2 representing the velocity of the mass, okay, m1, while z3 and z4 represents the velocity and displacement, the displacement and velocity of the mass m2. So the state of this system we are tracking is displacement and velocity of the two masses m1 and m2. Okay, so it yields us four systems of equation: displacement velocity for m1, displacement velocity for m2. So that gives us four states. Displacement of m1 is one state, velocity of m1 is another state, displacement of m2 is one state, and velocity of m2 is another state. So four states. So four states having four differential equations that we have seen like this, that can be represented by this system here. Okay, and we should not forget our input signal over here. So that's it. You need to practice more problems. So if you can solve other problem like this, get your hands around it, just apply the same concept that you've learned about today, and I believe you'll be all right. So this is going to be it about this problem for now. I hope you like this video and subscribe to my channel and hit the notification bell to stay updated. So we'll be moving on to another exam pass question, and we'll see how it goes. All right, bye.